Good afternoon and welcome to CRC's webinar series, Cooling the Capital Region from Models to Implementation. This webinar, Understanding Our Regional Heat Island Challenge, is the first webinar in the series. This webinar is organized by the Capital Region Climate Readiness Collaborative, or CRC, in partnership with the Sacramento Metropolitan Air Quality Management District. My name is Grace Kaufman. I'm the project manager at the Local Government Commission, serving as staff for CRC, and I will be your moderator for this webinar. A quick overview of today's agenda. I will first provide a brief intro to CRC for those of you who may not be familiar with us. Then the Air District's Climate Change Coordinator, Shelley Zhang, will provide an overview of the project and impacts of extreme heat on various sectors. After, Haider Taha from Outro Stratus will provide an overview of the heat island effect in Sacramento, how heat mitigation can be effective in reducing afternoon temperatures, and more. To finish, Jason Vargo from the California Department of Public Health will discuss how public health impacts on heat islands. Before we get started, I have a couple of logistical items to go over. Everyone will be muted except for our panelists. Due to the large number of participants, we ask that you type your question into the question box. Please feel free to submit your questions at any point during the webinar, and I will summarize those questions during the Q&A portion, which will follow Jason's presentation. If we don't get to all the questions, we'll ask our presenters to respond after the webinar, and we will share the responses in a follow-up email. This webinar will also be recorded and made available on our website along with the PowerPoint presentations. As I mentioned, this webinar is being organized by the Capital Region Climate Readiness Collaborative. CRC is a collaborative of local leaders seeking to build climate resilience through California's capital region. We bring together stakeholders from across sectors and jurisdictions to find regional solutions to address our shared challenges: drought, extreme heat, flooding, wildfires, and more. Our goal is to help the 6 counties of El Dorado, Placer, Sacramento, Sutter, Yolo, and Yuba, and the communities they encompass, thrive in the face of a changing climate. The Local Government Commission serves as the program administrator for CRC. If you have any questions or if you're interested in joining CRC, please don't hesitate to reach out to me. Now on to our featured presentations. Shelley Zhang works on the Sacramento Metropolitan Air Quality Management District's climate change mitigation and adaptation programs and has been participating in the Capital Region Climate Readiness Collaborative since 2013. She is currently leading a project to model the urban heat island effect for the capital region, focusing on transportation sector solutions to cool communities. You'll hear more about this project during the webinar. Shelley started her career as a writer and editor in Beijing, China, covering travel, food, and environmental topics, and made her transition to climate and energy with Greenpeace East Asia. She holds a BA in English from Harvard University and a Master of Public Policy degree from UC Berkeley. Dr. Haider Taha is president and scientist at Outro Stratus Incorporated. Previously, he was a staff scientist with the Lawrence Berkeley National Laboratory for 12 years, during which he was a deputy leader of LBNL's Heat Island Group. From 2004 through 2011, he was an adjunct professor of meteorology at San Jose State University. His research interests include urban and regional meteorological emissions and photochemical modeling for studying the interactions and feedback among meteorology, energy use, pollutant emissions, and air quality. He also focuses on developing and working with new generation, fine resolution meteorological models, including highly urbanized parameterizations. Applications of such models include, for example, studying urban heat islands and their mitigation, urban impacted, cloudiness and precipitation, heat waves and mitigation, local regional impacts of climatic changes, impacts of emission control measures, photochemistry to meteorology feedbacks, like radioactive forcing and fine resolution dispersion modeling. He has published over 200 scientific papers, reports, and book sections on these topics. Dr. Taha is a member of the American Meteorological Society Board on the Urban Environment, and in 2010 received the AMS Editors Award for the Journal of Applied Meteorology and Climatology. Our next speaker is Jason Vargo. Jason was born on a cold April day in Southeast Michigan. Today, he is the lead scientist for the Climate Change and Health Equity Program at the California Department of Public Health. In between, he was a member of the Urban Climate Lab at Georgia Tech. His work focused on figuring out how many lives could be saved by reducing the urban heat island in large US cities. The answer, quite a few. And a quick reminder to all of our participants to please type your questions into the control panel at any point during the presentation. And Shelley, you are up.
Good afternoon, everyone. My name is Shelley Jiang, and I work on climate change at the Sacramento Air District. Thank you for joining us on our webinar that will introduce and share results from the Capital Region Transportation Sector Urban Heat Pollution Project. This project is supported by a SB1 adaptation planning grant of $487,000 from the California Department of Transportation. Our project partners are the Local Government Commission and our consultants, Alto Stratus and WSP. We've also been pleased to have exciting project support from the Capital Region Climate Readiness Collaborative, SMUD, and the members of our Technical Advisory Committee, which is composed of transportation and planning experts from across the 6-county Sacramento region. It's been very exciting to work on this project for the last year and a half with these wonderful partners, and we're now wrapping everything up as our project concludes in February 2020. Now, you might be wondering, why urban heat pollution and why extreme heat? Extreme heat is one of the Sacramento region's main climate impacts. Even today, Sacramento has a higher rate of emergency room visits and fatalities due to extreme heat than the rest of California. And with climate change, this problem is only going to get worse. The Sacramento region is projected to face increasingly hotter average maximum temperatures in the summer by 2040 to 2060, with much of the region facing average highs of over 100 degrees, even up into the foothills of El Dorado and Placer County. Heat is maybe something that many people in Sacramento are already used to, but it impacts almost everything in our daily lives. Extreme heat exacerbates air quality and increases ozone formation, which many of you may know more commonly as smog. Heat also increases emergency room visits, heat strokes, and other related illnesses, such as worsening existing diseases like cardiovascular illnesses. Heat also presents major health challenges for outdoor workers, such as people in agriculture and utilities and construction, and also decreases the productivity of our economy, and especially our agricultural economy. Emerging research has also linked extreme heat to lower test scores and educational performance for students, especially in schools that have aging facilities, as well as higher rates of aggression and violence, lower birth rates, and premature birth. Heat can also take a toll on our energy system by increasing energy costs for residents and businesses and increasing the risk of grid instabilities with rising air conditioning demand. And heat also has an especially big impact on our transportation sector. Heat can expand and damage pavements due to a process called thermal expansion, causing asphalt and pavements to crack and buckle in extreme heat. Heat also can have a similar effect on railways, causing the railways to expand, which means that transportation systems must run their trains at slower speeds during extreme summer periods. In Sacramento, the overhead wire system that provides power to regional transit's light rail system is also vulnerable to temperatures above 100 degrees. And as a result, regional transit must slow the speed of their light rail during extreme summer heat periods. And also RT is also vulnerable to expanding tracks due to the heat. Finally, heat can also pose health risks to transit users who must wait for buses in places without bus shelters, and also to cyclists and pedestrians, as well as, again, construction workers, transit system employees, and staff who maintain vegetation outdoors. So for all of these reasons, heat is a major health risk to our region. Thus, to help the Sacramento region address the challenge of urban heat, we developed this project to focus especially on the artificial heat that's generated by the man-made built environment. This is known as the urban heat island effect. It results from the pavements, roofs, and other man-made surfaces in our urban environment. Dr. Haider Taha from Alto Stratus developed the heat island model for the region and then analyzed the effect of different mitigation strategies to cool the urban environment. And his research basically helps to understand which strategies are the most effective for different areas in the Sacramento region. And the project team also sought community input from residents in the Sacramento region to understand how people today are affected by heat and what kind of changes they would like to see. And finally, our project team with WSP also analyzed transportation plans and projects in the region to develop recommendations and strategies that they can adopt to become more resilient to heat. All of these results will be combined in our final report, which will be released in the next few months, that will provide science-based analysis of the regional heat island effect, the most effective cooling solutions, and the best heat mitigation strategies for the transportation sector. Now, before Dr. Hyder presents some of his results, I'm going to share and provide a quick overview of some of the heat mitigation strategies that we evaluated as part of this project. So one of the main strategies that we looked at is cool roofs. Cool roofs are different from normal roofs in that they reflect heat from the sun instead of absorbing it into the building. This helps the building become cooler and save more energy. A cool roof can help your house save your AC needs by 20%. And when a neighborhood applies cool roofs across the neighborhood, this can help reduce the urban heat island effect, which will then also reduce ozone formation in the neighborhood, improving air quality. A cool roof, by helping residents to stay cool with using less AC, can also help residents protect their health, especially if they are vulnerable or low income and cannot afford the use of air conditioning. And finally, cool roofs can benefit residents in that they absorb less heat and therefore have lower heat maintenance costs due to reduced heat stress and damage. And for many people who are concerned about how cool roofs might look, they come in all kinds of materials and can be adapted for all kinds of roofs, whether you have a modern house or a more classical house. Cool pavements was another main solution that we looked at for this project. Like cool roofs, cool pavements are considerably cooler than asphalt. Similarly, they work by reflecting solar heat away from roads and by not absorbing that heat. They can take a range of materials and fit a variety of functions, so you can apply it on streets, bike paths, playgrounds, plazas, etc. One particular kind of cool pavement is permeable pavements, which help to filter stormwater as well and can reduce localized flood risks. And cool pavements have a range of benefits, such as providing a cooler outdoor temperature for people that exercise or work outdoors, improving air quality, and improving driver safety, which they can do by being more visible at night. They can also help to reduce street lighting costs by reflecting more street light at night, thus helping cities illuminate streets with fewer light fixtures, and improving water quality by reducing the temperature of water runoff. And finally, cool pavements can also help cities reduce their pavement maintenance costs by being more resistant to heat damage and degradation from extreme heat temperatures. Here are some examples of cool pavements so that you can see the range of applications and functions they have. On the top left picture is a pilot project from the city of Los Angeles where they are painting the street with a special sealant that maintains a cool pavement. And you'll hear more about this project in our next webinar. And there's also examples of cool pavements being deployed in driveways, in parking lots, and in pedestrian crossings. Finally, the trees is a major cooling strategy for cities. Trees can help to clean our air, provide shade and comfort, save energy, filter stormwater, store carbon, and build neighborhood pride and social cohesion. I won't go too long over this topic because I think trees are a very well-known urban cooling strategy. Our final cooling strategy that I'm going to highlight today is zero emissions vehicles. Zero emission vehicles may not be known to everybody as an urban heat island reduction strategy, but in fact, only 12 to 30% of the energy that you put into a conventional gas or diesel car is used to move it down the road. Conventional gasoline cars lose up to 60 to 75% of their energy as waste heat from the exhaust pipes. That's a lot of heat coming from a car. And you'll know if you ever touch your car hood after you finish a trip that the car hood is very hot to the touch. An electric vehicle, on the other hand, emit only 20% of the waste heat compared to the combustion engine vehicles. So by adopting electric vehicles widely in our region, we can help to reduce the urban heat island effect and protect also the health of people on the highways that are exposed to the pollution from exhaust pipes. Widespread adoption of electric vehicles, especially in our low-income and vulnerable communities, can help to protect public health and reduce the heat island, and which is why the Air District has several programs focused on improving electric vehicle adoption. And finally, here's a quick snapshot of some of the community outreach that we did as a result of through our project. We asked people about their exposure to heat at home, and we asked about people whether they or not they had cooling access. And so we found a large disparity in access to air conditioning at home for homeowners and renters and across counties. And so these highlight which residents are more vulnerable, and these results will be reflected in our project. And also our research, our community outreach, we found that, for example, low-income residents were more vulnerable to heat exposure at home, at work, and during their commute than higher income residents. And all of these results will help to inform our recommendations. And now I'm going to turn this presentation over to Dr. Taha at Altostratus, and he will share with us his project findings.
Okay. Thanks, Shelley. Thanks, Grace. Can you hear me?
Yes.
Okay. Well, hello, everybody, and thank you for joining and listening. My name is Haidu Taha, staff scientist at LBNL and scientist at Altostratus. Next, please. I guess we're having a little problem controlling here, but next slide, please. So this being, I'm wondering if I can control it, maybe, no. This being the first of 3 webinars, I thought I'd run quickly through some definitions or concepts that we're going to be using later. The first one is what's an urban heat island, UHI, and what's an urban heat island index, UHII. Simply stated, the UHI is a temperature difference between 2 points, and these 2 points could happen to be urban versus non-urban. And there are different conditions. For example, the reference point could be varying over time, depending on wind direction, depending on different factors. But the bottom line is that the UHI is an instantaneous temperature difference between these 2 points. If you accumulate, in other words, if you total up, if you sum up the UHI over a certain period of time, let's say an hour, a day, a month, a year, 10 years, then you have what I call a UHII. It's a simple distinction. So the UHII, from my perspective, is an instantaneous indicator. The UHII is a cumulative indicator. What is the purpose of the measures we're talking about today? Simply stated, it's just reducing air temperature. So as a resident in any neighborhood, if the weather is hot, all you really care about is you'd like to have the outdoor temperature as well as indoor, but you want the outdoor temperature to come down a little bit. You don't have to, and you don't really care whether your neighborhood is warmer than some other part of the city or some non-urban area. All you want is to have some cooler air. And so if that's the case, the question becomes, why even bother about UHI and UHII? The answer is that these are relatively considered planning tools. They are yardsticks or measures of how much cooling you can realistically expect to have in your location. Is it 1 degree, 2 degrees, 3 degrees? It's some sort of an indicator as to how much cooling you could achieve where you are. And conversely, it's also a measure of how much the urban area has altered the temperature field in the region. Then there is the question of air temperature UHI versus surface temperature UHI. To keep it short, I just want to say that in this study, the UHI and all the metrics and derivatives we're going to be talking about are based on air temperature. not on the popular hotspot type of analysis that come from remote sensed data, satellite imagery that show, for example, red hot roofs surrounded by cool trees that are in blue colors. That's not the point here. We are looking at air temperature as the main driver to thermal comfort, to emissions, to air quality, and other aspects. And the reason why I'm bringing this up is because the spatial patterns of the temperature that you're going to see when you analyze air temperature, urban heat island, are very different from the spatial patterns of the skin surface temperature that you see from aerial photography, let's say. And if you look at the observational weather data from the network of monitors in the region, they'll tell you the same thing. And finally, why is this important? Is mainly because studies have shown that when climate changes, whether in the short term, let's say, heat waves, or in the future, it tends to be exacerbated in urban areas, tend to be worse within the urban areas. So that's something we need to consider and plan for. Next slide, please. So real quick, the technical task in this project involved doing detailed land use land cover analysis for current conditions as well as future projections and characterizing the physical properties of the urban areas accordingly, carrying out detailed observational weather data for the past few years, carrying out base atmospheric modeling and doing detailed statistical model performance evaluation to make sure we're happy with the model. Then two main chunks. One is modeling of mitigation measures under current conditions of climate and land use, and then modeling mitigation measures under future conditions of climate and projected urbanization. This project, we decided to look at 2050, both RCP 4.5 and 8.5, and then opening the floodgates for post-processing, post-analysis, different metrics, different thresholds to characterize urban heat and mitigation from many perspectives. Next slide, please. The modeling in this project was based on a 10 domain or 10 grid configuration, as you can see in the upper left part of this slide. And the resolutions of the domains ranged from 54 kilometers all the way down to 500 meters. What I would like to mention is if you look at the bottom left figure, you see these white rectangles. These are the 500-meter domains. And what I want to say is that the positioning, the location of these domains were decided based on feedback we got from the cities, the communities in the area, the Air District, LGC, and the project technical advisory committee. You can also see them on the right side. And for many different reasons, for example, some areas are projected to urbanize quickly, or some areas already have a heat problem, or there are roadway MTP projects, and so on. Next slide, please. So the first thing was to characterize urban heat in current conditions, and there are many different ways you could do that, different metrics, different, I would say, ways to represent urban heat. And what I'm showing you here is the urban heat island index as a composite of 6 different tiles, 6 different regions for a example period, which is July 16 to 31 of 2015. And this is an all-hour UHIN average. In other words, it includes day, night, and there's no particular distinction here. Although the project has produced all kind of different UHINs, different times of day, peak, nighttime, etc. But here I'm showing the all-hour average. So you can see some of the information in the figure, which also shows these outlines of AB 617 communities that were identified by the Sacramento Metro AQMD. And these are letters A to J. I'm just showing a few of them here. The numbers, the bold numbers, next to each letter are the temperature equivalent of the UHII. So, for example, if you're looking at community D near the top, 3.9 means its UHII equivalent is 3.9 degrees Celsius, meaning it's on the average 3.9 degrees Celsius warmer than the upwind reference point, which happened to be near Davis in this case. I mentioned tiles. You can see 6 of them, namely these rectangle. It is, I mean, the reason I want to mention this is that this looks like a consistent single map, where in fact it's a composite. In other words, the UHII within each of these tiles was calculated independently of the other. It was calculated based on its own upwind, time-varying reference point that have nothing to do with the others. And so this might cause some confusion because what you're looking at here is not temperature, is UHII, it's temperature difference. And so you might be tempted by looking at this figure to think that Auburn on the upper right is warmer than, let's say, communities A, B, and D. That's not the case. Again, this is a temperature difference. So what this is showing you is that the temperature difference between urban Auburn and non-urban Auburn is larger than the temperature difference between, say, community D and its upwind non-urban reference. Next slide, please. The other thing we looked at was to see how the urban heat island index and urban heat island change into the future. And so on the right side, I'm showing some averages. On the horizontal axis, you see different domains or subdomains. And on the vertical axis is the change in temperature, which is, in this case, an increase for RCP 4.5, 8.5 in 2050. And obviously, there's a range, and there are different directions it goes. But in general, it's between 0.3 and 0.8 degrees Celsius. And keep in mind, this is an average over all hours and an average over all urban grid cells or urban areas within each of these subdomains. So what I'm trying to say is that the actual change could be a lot larger than this. This is simply an average. On the left side, I'm showing how it would look like, spatially, or how these changes will look like. So you can see the outline of Sacramento, Yuba City, Davis, Woodland, etc. You can see that in the middle there is a number plus 1.36, which is saying that in 2050 RCP 8.5, the current urban areas that are currently urbanized warm up by about 1.4 degrees Celsius for this particular period, July 1631 in 2050 relative to present. And this is the climate effect only, because these urban areas already exist, and we're assuming that nothing changes there. However, if you look at the outskirts of each of these urban areas, for example, Sacramento or Davis, etc., you see that the warming is a lot higher. In this example, it's 2.77, which is double the amount of the central area. The reason is because these outskirts are influenced by two things, two effects. One is the land use change, urbanization, and the other is the climate. So these are areas that are currently non-urban that became urbanized by 2050. And so if you do simple math, 2.8 minus 1.4, that's double, which tells you that the effect of land use, land cover, urbanization locally is in the same magnitude of the projected local climate change effect, which is important to keep in mind when designing urbanization measures or designing mitigation measures. Next slide, please. Next slide, please. Thank you. So real quick, Shelley already previewed some of these measures. So urban-wide and transportation, we're looking at the two sides of the equation. So urban-wide looked at cool roof, pavement, vegetation cover, cool walls, EV ownership, and solar PV. The transportation corridor focused mainly on increasing albedo and electrification. Next slide, please. So the first thing was to look at the temperature change resulting from these mitigation measures. And here we're looking at the cooling effect of a measure called case 10, which is simply a small increase in albedo in urban areas based on technical potential. If you look at the upper left part, it shows you a typical pattern of cooling following the urban areas. You can see all these cities around the satellite city as well as the main urban area in the middle. The cooling, of course, depends on weather conditions, on the amount of implementation, the measures, the combination of measures, etc. But it's typically between 1 to 2 degrees Celsius, and it goes all the way to 3.5 degrees Celsius at certain times and at certain small locations. So just to give you a range. And a lot of details are provided in technical reports showing you how each area under each weather condition or under each time of day, how the temperature response is. The main figure in the middle of the slide is an example of how modifications in one urban area can affect the other. So, for example, if you look at the, well, I can't point. I don't know if you Do you see my cursor moving? Do you see my cursor moving? Hello? Is it moving?
No.
Okay. Anyway, so for example, if you look at the middle area near the top of this big figure, you see the cities of Yuba City and Maryville. You see these dots or small circles everywhere. These are the locations or grid cells where albedo was actually modified. And the darker the circle, the higher the albedo modification, as you can see in the legend on the left side. The shades of blue are the corresponding temperature changes. Again, the legend tells you how much that is. The point is, if you look at the wind direction in the upper left figure, coming from the northwest, going through Yuba City and continuing to the southeast, you can see a corresponding plume of cold air going to the southeast direction as well. If you look at the area near Folsom Lake, which is near the right side of the blue urban area, you see the wind on the upper left slide going southwesterly. It's coming from the southwest, going to the northeast, and you can see in there also a big area of temperature decrease without any modifications. And you can look at that figure and see how the wind direction changes and how it pushes the cold air from one area to another. The takeaway is that if some areas do modifications locally, they can still benefit the areas downwind. The question is how far that effect is. Turns out it depends again on the amount of modification, wind direction, wind speed, etc., but in the order of magnitude of 2 to 4 kilometers, meaning by the time a cold air leaves an urban area, it travels 2 to 4 kilometers before losing half of its cooling effect. The reverse is true. Actually, that's the reason why we're doing this. Heat is also transported. So urban heat from one area can be transported downwind 2 to 4 kilometers to reduce or to become half of what it was in the urban area. And it's nobody's fault. It's because there's an urban area upwind, you still inherit the heat. And that is something we use later on to show how different communities can assign responsibility. What happens if your neighbor upwind does something versus transport the heat versus what you do locally. Next slide, please. The other thing was to look at whether we can convert some of these temperature changes or derivatives into some indicators on impacts on public health. So I'm looking at here is the impact of a scenario called Case 31, which is a combination of albedo and vegetation cover increase at 5 p.m. on every day at 5 p.m., and how it can impact the National Weather Service Heat Index, which is a measure to use to issue health warning. If you look at the upper left figure, you can see that there are these dotted lines. The heat index is defined at 80, 91, and 106 degrees Fahrenheit, corresponding to caution, extreme caution, and danger levels. And the blue line that you see there is the base case. The red line is the modified case or the heat mitigation scenario. So you can see in 2013 to 2016, and there are in this time series 425 p.m. points. At every one of them, the mitigation measure decreases the heat index. In some locations, unfortunately, I can't point with my cursor, but you can see that if you look at any of these dotted lines, the mitigation measure brings the heat index from one category, one warning level, to one that is lower than it. In the future, on the bottom two time series, on the left side, you see 2050 RCP 4.5, on the right side is 8.5. So you can see that the top dashed line, whereas there are no exceedances in the danger level in 2013 to 2016, you start seeing exceedances in RCP 4.5, and the exceedances do start increasing in RCP 8.5, the blue line going above the dashed line. You can see the effectiveness of the measure in the red line is that it prevents it from going over that threshold, or conversely, it brings down the exposure or exceedance in danger level to the lower level, which is, in this case, extreme caution, or from extreme caution to caution. So it has the ability to mitigate sometimes 100% the exceedances in the heat index. Next slide, please. I think there's no time, so I'll just say here that another implication of the cooling measure is its ability to reduce heat wave days. These are examples at different locations for 3 heat events in 2013, 2016, and you can see that the proposed mitigation measures can decrease heat wave days from 5 to 1 or 3 to 0. It's a whole range, but quite significant decrease. Next slide, please. I'll probably have only 2 more slides. Here we're looking at the impacts of mitigation measure on future microclimate, which bears quite is similar to what we see in current climate as well. And this is an example for Dorado Hills and Auburn, arbitrary or random examples. On the top, you see an average at 3 in the afternoon, and the bottom is an average of all hours. And these are the changes in temperature for different time periods on the horizontal axis for different measures listed on the right side. And the bars, the colored bars, each one correspond to a different measure. So you can see the main point, the main takeaway from this is not so much the absolute amount of change or which one is better than the other, but the ranking. You see there's number 1, 2, 3, 4 on the right side of each figure. These are the ranking of the measures. So, for example, at 3 p.m. on the top graph, you see number 1, which is the best measure, is actually a combination of albedo and canopy cover. Whereas if you look at the bottom one, the best measure, number 1, is actually the increase in canopy cover. Why? Because all hours include nighttime, and nighttime is a time when vegetation cover also has an effect. Whereas during the daytime, only albedo and, reflective materials have an effect. So basically the bottom line is if you look at the ranking, it differs from one location to another, from one time of the day to another, and from one measure to another. So these are things that some sort of a matrix that we have to keep in mind when looking at mitigation measures. And I'm going to talk about that in the second and third webinars. Finally, next slide, please. Looking at the impacts of smart growth on future urban temperatures. And since we don't have time, I'll just say that the upper 2 figures show you in the red the difference between business as usual and smart growth, which we define here as 15% less urbanization. On the bottom is the average reduction in temperature at 3 p.m. in the afternoon. So you see an avoided warming of anywhere between 0.2 to 0.4 degrees Celsius. And at all hour averages, you see a reduction or avoided warming of up to 1.5 degrees Celsius. And the reason why is this larger than the 3 p.m. is because, again, the impact of urbanization is larger on nighttime heat island than on daytime heat island, which is a typical definition of the urban heat island. Anyway, I will stop right here. Thank you very much, and I'll go to Dr. Jason.
All right, thank you, Dr. Taha. Jason, are you there?
Yeah, can you hear me? This is the first time I've spoken.
Yes, we can.
Okay, great. So I think I now have control, and I just want to say thanks for inviting me to talk on this webinar. I've been participating with the advisor a little bit through the technical advisory committee for this project, and it's been exciting to use some of my expertise in a practical way in Sacramento. A lot of this work and this presentation I've given many times to a lot of different audiences, so hopefully it makes sense. If there's anything that you have questions about, please feel free to add them to the questions box, and I'll try to answer them in the question and answer section. So I'll try and go rather quickly, but in essence, I'd like to use this piece, which came out when I started putting this together several years ago, but it was a reprint of a New York Times story that originally appeared in the New York Times over 100 years ago. And it really just talks about heat in the city. So the idea that the constructive materials of the city are creating environments that are hotter than would otherwise be there is not something new. I really like the language that this piece used, and it sort of follows many of the health impacts that I'll talk about. So the first thing that you notice, or one of the first passages in this article was that the brick walls of the houses reflect the hottest rays of the pavement. The pavement returns them with such good interest that the wayfarer realizes all the wretchedness of passing between two fires. The constructed materials are called out by name here, the pavement, and the rays of the sun and the way that they're interacting with those materials is obvious to people. And this was a photo that aired with the story. There's no canary in the coal mine, but there are horses in the street in this case. That this horse was overcome by heat, you can see in the bottom left corner. It's important to note that not only were the urban environments so hot that horses were dying, but the sort of character of the people that are out in the street and experiencing this heat, the same heat that these animals are experiencing, are children, workers, people of color, and these are not the Wall Street New Yorkers necessarily. And the same sort of attention to vulnerable populations needs to be given to urban heat and health impacts today. So obviously, one of the first ways that it manifests is that heat itself can be deadly. So another way is that the atmosphere undergoes a befouling process with floating dust. And so this is really about the air quality. Shelley mentioned this as well, that, I'm sorry, it's sort of advancing without me doing things. Oh, sorry. So the air quality itself will also be changed as more heat and more energy is trapped in urban areas. And so, as Shelley mentioned, that can manifest in ground level ozone, which is a acute irritant for lung tissues and can exacerbate existing conditions, respiratory conditions for people, make it difficult for breathing. And even though this picture is likely an inversion, the air quality in urban areas will be degraded as the urban heat island is exaggerated. And then this phrase I put in there to really capture something else that might be happening as areas get warmer, and that has to do with changes in plant behavior as temperatures and climates change. We see, the hardiness zone for plants moving north. The latitude is sort of expanding. The range of these plants are moving north, but we also see sort of production of pollen and that plant behavior changing as well. And so this is a study that looked at 4 different sites moving from rural to urban from top to bottom. And you can look at the pollen levels, which are the red sort of plots at different along the course of a summer. And you see that the season is really extended in these suburb and urban areas. And also the peaks of the pollen season are much higher in these urban and suburban areas, not only for the presence of additional heat, but of course, there's a phenomenon that's sometimes referred to as the CO2 dome of cities. And so this increased CO2 levels that exist perhaps around metropolitan areas as opposed to the global CO2 concentrations may also be contributing to this flourishing of plants. It's important to note that even though there are more vegetation in the top 2 settings, you see the higher levels, especially for these plants which are invasive and opportunistic in these disturbed landscapes of urban and suburban areas. And the atmosphere is not merely charged, but overcharged with these different diseases. And so it's important to note that many diseases that we see popping up are also likely to change as temperatures change for urban areas. One that has been studied and projected forward is the appearance of kidney stones, mainly through dehydration, but we have many other studies that have shown that we see increased hospitalizations and visits to the emergency departments for kidney dysfunction, electrolyte dysfunction, dehydration as temperatures rise. And this is likely to exist in urban areas more than surrounding rural areas. Someone just asked about flu season, which I don't know exactly how flu season would change. But one infectious disease that we do expect to change, or some infectious diseases that we expect to change are those carried by vectors. And malaria is an important one, but of course in California we're often more concerned with West Nile virus rather than the global issue of malaria. But it's important to note that not only will the range of the vector perhaps increase, north to south, similar to those plant ranges changing, but also in urban, insects within urban areas may their biology may change, and the parasite inside vectors may change in hotter urban areas, meaning that it would take a shorter time for insects to become infectious. In this case, with malaria, we see that temperature, the extrinsic incubation, that is the time that it takes for the mosquito to become infectious, is very dependent on temperature. And so warmer temperatures tend to mean that mosquitoes become infectious much sooner and much more quickly than in colder temperatures. And importantly, it will not just affect physical health or infectious disease, but it's important to note that the general effect is decidedly discouraging and depressing. This is something that was noted in this article from the 1800s, as I mentioned. But we also see mental health outcomes changing as temperatures get warmer. Some studies have looked at emergency department visits related to mental health, often in the form of self-harm, for example, or accidents and injuries. One study that I like to talk about, I haven't put it in here, but just the sort of hot-temperedness of people tends to, the tempers get shorter as the temperatures get warmer. And there's an interesting study that looked at the propensity of opposing pitchers to throw a beanball after a member of their team had been thrown at by the other team's pitcher. And on warmer days, they were more, they went to that reaction of violence a little more quickly. But in general, we do see increased mental health outcomes as temperatures get warmer, and that's likely to exist again with the urban heat island in city centers. And it's important to note that the houses that we live in are generally sanctuaries from the outdoor heat. So when people see a horse dying on the street, they would turn inward and go to the houses and seal them up. This is not only, I think part of the mental health aspect that was being described in terms of spending so much time being indoors, but it also puts us in close contact, so infectious diseases may spread more, and of course indoor toxins may be a problem. Now, when we do this research in place, like in real, and try to prove these methods, proof of concept in real world, we're often relying on studies that look at relationships between temperature and mortality and morbidity. It's important to note that we see differences in people's responses to temperature, the health response to temperature, based on the ability of a population to sort of adapt and cope with different temperatures and what they're familiar with. In this case, this study looked at 11 cities, some northern cities, some southern cities, and we see different shapes in this curve where you have elevated relative risks at the far left, which are the coldest temperatures, and the far right, which are the warmest temperatures. But you'll see that the slope of that curve from the trough, which is that minimum mortality temperature, changes for northern cities and for southern cities. In this case, you see northern cities are the red curve, and they seem to be more sensitive than the southern cities to hot temperatures. And the southern cities tend to be more sensitive to the left of the trough, to those colder temperatures, than to southern cities. And that's in part because of adaptations that have been built into homes and buildings and just adaptation practices and culture over time. And we're trying to incorporate those more and more into our studies. That last figure looked at general response to a number of different temperatures, or any temperature, but in general, we also look at the hottest periods of time as well. And this was a very famous heat wave. That looked at extreme or excess mortality to extreme heat. And the way that we do that is we often compare mortality during a heat wave to mortality in the same time of year from the year before or the time period before and after. In this case, you can see this is the Parisian temperature from 1999 to 2002, and then on the bottom you see the number of deaths that occur on a daily basis over that time in the summers before 2003. And when you look at 2003, you begin to see the temperature in red, climbing and staying elevated for a long time, and then the sort of epi curve, the number of deaths in that bar chart following along with that. And so this type of research, looking at episodes, also gives us a lot of evidence on which to base modeling efforts when we try to predict how changing the urban heat island will protect human health. I just want to put up some of the work that I worked on, as was mentioned, with the Urban Climate Lab out of Georgia Tech. This was a 3-year CDC-funded grant where we modified the land cover in urban areas and then put that into a climate model and looked at future summer temperatures and how that would change mortality in those cities. That's the paper on the left. And then there were 2 applications of it where cities had, or nonprofits in the case of Texas Trees, pursued using that methodology to help them plan for adaptation measures. I don't want to go into the results, but these could be useful resources for local governments if they're choosing to try and pursue this. So these are examples that take the ideas about changing land cover and reflectivity and vegetative composition of an urban area, and then translating that into health impacts in a real way. And I don't want to, there's a couple more slides that I won't cover, but they're just examples from the Louisville instance. But I do just want to make sure that I make clear that it would be easy for a knee-jerk reaction to the urban heat island to say, okay, well, then we need to direct development to less urban settings, or to look for these rural areas that maybe have more vegetation already. And I would caution against that and say that part of accomplishing larger climate goals is to direct development into more compact growth. And that's one reason that I think it was the last slide that Hader showed, it's so useful to understand that smart growth is actually offering bigger temperature reductions than business as usual. And I know Shelley mentioned zero emission vehicles, but of course compact growth facilitates no vehicle transportation options, which are even healthier and better for the climate. And so we want to make sure that we can encourage land uses that facilitate compact development and smart growth, and at the same time ensure that those new developments have land covers that don't exacerbate the urban heat island. That's really the sweet spot between those 2 things. And so that's basically about all I have at this time, but I'm happy to take questions. And again, thank you for inviting me.
Great, thank you, Jason. That was great. We do have several questions in about 5 minutes, so we'll try and get through as many questions as we can. And as a reminder, any questions that we don't get to, we'll send to our presenters, and it'll be included in the follow-up materials, along with the recording and the presentation slides. So the first question that we have is for Dr. Taha to please explain the rankings on slide 33. And I'm going to try and bring that one up again. So Dr. Taha, do you think that you could describe a little bit about this, what the rankings mean and how to read that? Are you there, Haider?
I forgot to unmute myself. I'm sorry. There are many ways to actually. There was a slide following that showed a lot more information. But let's just look at this slide. If you look, for example, let's look at a random example. 1500, the top figure at the very right end. You see, let's say 1, 2, 3, 4, 5 different bars. Each one corresponds to a mitigation measure. So what it is saying basically is that in that time period, which happens to be, if you read at the top, 2050 interval 7, that means it's sometime in September. The ranking of the measure, the most effective measure, the one that produces the most cooling, is number 1, which is a combined albedo canopy cover measure. The next one that produces, the next most cooling measure is number 2, which is large canopy cover increase. Then number 3 until number 5, which produces the least cooling, is a small albedo increase. So that's the kind of our ranking that we were talking about. I'm not sure what the question is. For example, if you look at the bottom, when you look at all our averages, the ranking is different. Why? Because the albedo measure tend to work best during the daytime, whereas vegetation canopy works during daytime and nighttime, so it has more of an impact on all hours. Could you show the next slide just really quick? I'm not going to explain it. No, the one after that, please. Oh, wow, where is it? Oh, yes, this one. So you can see this is a summary of the effectiveness of measures in different areas. You see the top of the slide, a different geographical area. On the left side, you can see different times of days and different applications. So everybody tends to look at temperature reduction in a different way. The question is, what's best for my location, let's say, at night? What's best for my location if I want to combat heat waves? That's the kind of information that figure is showing, the ranking. I realize there's not much time, but please, you can have my email, and whoever is asking me the question, I'll be happy to follow up. But I hope that I did explain what these rankings are.
Thank you. All right.
Okay.
And then, Jason, this one is for you. What is the #1 policy recommendation, in your opinion, for local governments to reduce heat mortality?
The #1 recommendation?
Yes, not #2, just #1.
Okay. Well, it's not just for heat mortality. I mean, I think one of the best recommendations for anyone who's trying to prepare for any health impacts is to understand the vulnerabilities that are contributing to that, that make people more likely to show up at the emergency room before others. And if it could be for heat, it could be for floods, it could be for an earthquake. It's all kinds of emergency preparedness. It's all kinds of chronic diseases. Understanding, why parts of your city are systematically, suffering from poorer health outcomes than you would want or than you expect is the #1 way to sort of make progress. Because the healthier your population is when it's cold, the less likely they are to show up at the emergency room once it starts to get hotter. And so working with your public health department to identify which communities are suffering from the most, and understanding what the root causes of those inequities are is probably the #1 recommendation I would make about sort of addressing any climate-related health hazard.
All right, folks, we are at time. Thank you so much, Shelley, Dr. Taha, and Jason for joining us today. And thank you to everyone who was able to participate in this webinar. We hope you found it worthwhile and valuable. As a reminder, the webinar recording and PowerPoint presentations will be shared via email and also posted on CRC's website. If you have any additional questions, please don't hesitate to reach out. And that concludes our webinar. Thank you again for joining us today.